This problem involves a beam that is twice statically indeterminate. What this means is the number of reaction forces exceeds the number of available equilibrium equations by 2. In simpler problems, it exceeds by 1. So the given beam is supported by 3 rollers and 1 pin at A, and it is twice statically indeterminate. And one way to see it is we say if we remove the constraints at B and C, we will end up with the basic simply supported beam, which is statically determined. So 2 constraints need to be removed, and therefore we refer to this beam as twice statically indeterminate. Well, let us indeed remove the constraints. We'll replace them with the reaction forces RB and RC, and then we say that the conditions for finding RB and RC are simply VB equal to 0 and VC equal to 0, simply because in the original beam we have rollers there, and rollers imply these 2 conditions. Of course, this problem is symmetric. Because it's symmetric, we can claim immediately that RB equal to RC, and I will call them simply R. So now our task to find R. So the first part of the superposition, I will be interested in looking at the distributed load. That's the table for the distributed load. And I will be evaluating the displacement at B. I will use this formula. I will use length 3L rather than L. And I will be evaluating it at x equal to L, or this point. Now, just out of curiosity, I calculate V sub C. V sub C is evaluated here. So in my beam of length 3L, the coordinate of C is 2L, and not surprisingly, I get identical results. And this is again a consequence of symmetry. The second superposition involves 2 forces R. There is a table for 2 symmetrically applied forces. And this table, as you can see, it has 2 branches. And what I will do, I will use this branch, and B will have the coordinate x equal to A. So here we are. Minus, because my forces are up, forces here are down. Instead of L, I will substitute 3L. Instead of A, I will substitute L, and I evaluate at x equal to L, and here's the answer. I'm not going to evaluate the deflection at C. Not that difficult, right? I probably will have to use this branch in order to do it, but I simply trust my instinct saying that the deflections at these 2 points are the same. Now I superpose the 2 solutions, and here's the deflections. So this one is due to the distributed load, this due to the pair of forces. I said this deflection equals to 0, and I end up with the answer for the reaction force, either at B or C. And with this force known, first I acknowledge that this is part of my answer. And then I draw the free body diagram for the entire beam. The reactions at the ends are equal because of symmetry, and a simple equilibrium equation for the forces gives me the value of the reactions at the outer support.